Hello everyone. In the next few videos, we'll be looking at ensembling methods. These are basically methods that take a whole bunch of different classifiers or regression models and try and combine them to make a single unified model that's better than the individual models. These methods can be used with any type of model, so logistic regression or naive Bayes. If you're doing classification, regression, you can use linear regression or regression trees. But very, very often, ensembling is used in conjunction with simple decision tree models or regression tree models, which actually gives quite powerful classifier or regression models. We'll look at a whole bunch of different ensembling methods. The first one we'll look at is bagging. Bagging is quite a simple method, but it turns out to work really well. So let's build up the intuition for this method. So imagine we have some training data and we've stacked all our training points into a design matrix. So we have this matrix X where, for example, the first row would simply be the first training input vector. Normally we take the transpose of that because we think of the training vectors as column vectors. The second row is the second training item, and so on. And we have n training items. That's the normal convention, n. Okay, and together with the inputs, the different features, we of course also have our output labels. Okay, so y1 would be the output for the first training item, y2 would be the output for the second training item, and so forth up to yn. Okay, and we can stack all of that into one vector y. Okay, again, y has n training points. So this is our training data, and we could fit a model to this training data. So maybe we call that model f, and it has input x and some parameters theta, and we can fit that to the data. And there might be problems with this model. For example, if it's a decision tree or a regression tree, if this is a regression problem, then this model could maybe overfit to this training data set. So let's look at an example of how we could overcome this problem of overfitting. And we will look at kind of a idealized setting, which won't happen in reality. And then we will see how we can actually replicate that idealized idea in a real setting. So let's say we're in a situation where we've collected the n training data points, and this was the model, right? We collected n training items, each with a corresponding label. Okay, for now, let's think of a regression problem. Okay, so each of one of these values is a continuous number. Okay, and we fit the model to this data set, and it massively overfits. Okay, imagine what we do then is we go out and we collect another data set. So it's from the same problem domain, but it's a completely different data set. Okay, again of n points. Okay, so we go out and we collect this data set, okay, with multiple different training points and with multiple labels. Okay, and then what we do is to this data set we then fit a model. So let's maybe call this is x2. It's our second design matrix because we went back, we collected another data set. It also has endpoints. Okay, and then this is maybe y2. Okay, our vector of target values. Okay, also of endpoints. So we've got an x2 and a y2, and to that we fit another model. Okay, and let's call that model f2. It has its own set of parameters theta2. To make things simpler, let's maybe think of the first matrix that we got as just the first data that we collected, and we fit a first model to that. Okay. Now what we do is we go back and we collect yet another data set. Okay. So we get another data set again with endpoints. Okay. And this is maybe x3, and we call this y3. And what we do is we fit a third model to this third data set. Now, this data set and this data set and this data set, they're all different data sets, but they of course come from the same problem domain, the problem that we're trying to solve. Okay, and we continue to do this. Okay, we collect a fourth and a fifth up to maybe capital B, different data sets. Okay. Okay, and in each of the B data sets, we fit a different model. Now, in the end, we want to make some prediction. Okay, and then what we're going to do is we're simply going to take the outputs from all of our different models, from our first model up to the Bth model, and we will just average the outputs from all of those. So our final prediction, fx, okay, theta is now the combination of all the parameters of all the different models, is simply the average from our B models. Now, why does this help us at all? The idea is basically that if we have one model that overfits to a specific training data set, then if we kept on getting different data sets and kept on going back and collecting more data, then if we then in the end averaged all of the outputs from the models, from all of the different models, then we will get a more robust prediction. And I think that idea makes a lot of sense. Now the problem is I described this very ideal setting where we have flowers and butterflies and everyone is just happy all the time, and where we can just keep on going back and collecting more data sets. Each time we collect endpoints and we fit a model to that, and we can keep on doing that. But in a realistic real world setting, that won't be the case, right? In a real machine learning setting, we start with one data set, and that's it. We need to fit our model on that data set. So what I will explain now is a way that we can use one data set and basically emulate this idealized perfect world situation. So let's start with the single training set that we have. We've got our design matrix X that consists of our different training data points, and then we've got our target vector Y, which again consists of our n target values. Okay, and we only have n training data points. We can't go back and get more data. Okay, so here's the strategy. What I will do is I will construct a new design matrix. Let's call it x1, and we have the corresponding target vector y1. And the way I construct it is as follows. What we do is we go to x and we pick one of the training vectors and target values randomly. So let's say we pick this vector here. That's our input, and then we've got the corresponding output here, and that will be in x1, that will be our first training item. Then we do that again. We go back to our data X and we grab a random training item, a random input output pair. Maybe we pick this one. Okay, and that then becomes our second training item in x1. Okay, we do it again. We grab a random training item from X. Maybe it's one here. Okay, and that becomes our third training item. Okay, and you continue to do this. You do this with replacement, which means that we can again pick a random item, and maybe we pick again this blue item that we already have in our x1 design matrix. Okay, and we continue to do that. We do that until we get n points in our design matrix x1. And then what we do is we fit a model to this data set, this x1 data set. So we fit a model and we get our first model, f1. Okay, maybe you can guess what we do now. We repeat this process. So now what we're going to do is we're going to construct a second design matrix, x2. Okay, and we have the corresponding output values, y2. Okay, and again we go back to our original input data from the fixed data set that we have. We sample a random training point. Maybe we start with the orange one. Okay, then we pick a completely different item. Maybe we call it red. Okay, and so forth. Maybe we sample another blue item, and so on. Okay, again with replacement. So you could in one of these design matrices, you could maybe have 3 of the orange vectors. Okay, and then what do? We continue to do that up to n training data points, and then we fit our second model F2 to this data. So we get B different models, okay, each with its own set of parameters theta, okay, and then we're done. Okay, not quite. To get the final prediction from our model, what we do is we average the outputs from all of our different models that we've trained. That's what we would do typically in a regression setting. So everything I described here is generally what you would do for regression. For classification, you can follow a very, very similar strategy, but instead of averaging the model outputs like this, what we can do is we can have each model vote on which class a specific input belongs to. Okay, so for classification, we can take a majority vote. So what we do is, for classification, we will have B different classifiers. Each one of them would classify the test point as one of the, let's say, capital K classes, and you simply check which class is predicted most often by my B classifiers, and that then is the final output from the model. You can be slightly more clever, and you can have a weighted majority vote, where you look at the probability from each of your different classifiers assigned to that test point, and you weigh their classification output by the probability that they're assigned to that point. And that's bagging. It's a very, very simple approach, but it turns out to work really well. I should also mention that this idea of taking one fixed training set and using that to construct multiple other sets is actually a little bit more general than just bagging, which we use for model combination. This is an idea normally referred to as the bootstrap, where you use one training set to generate multiple different sets, and then you combine statistics or predictions on all of those different sets to give you some more insight. In the next video, we will look at how bagging can be extended, specifically when it's used with trees, decision or regression trees, to give you even better predictions.